little bit of introduction here. I got started on all this in 1962 when the Tree Ring Lab at Tucson and the National Park Service developed a project to do a more or less complete tree ring sampling of Batatacan ruin at Navajo National Monument, and I was lucky enough to get to do it. The Park Service was concerned about the deterioration of the wood in the site, which they naturally are still concerned with, and wanted to get it sampled, get a sample from each log before it became impossible to really sample them any longer, which I was happy to do, but I wanted to explore the range of information on past human behavior that you could extract from a comprehensive collection of archaeological tree ring samples with maximum control of provenience, where the samples came from, where the logs were, and preservation and stuff like that. And Batatacan was the ideal spot. If any of you've been there, you know that there's a lot of wood still there, and I was lucky enough to take cores out of most of those. And I sort of fell in love with that part of the world. The landscape there is incredible, and the archaeology is just as good. So I just managed to ramify studies of different things up there for the rest ever since into different topics, of which I'll cover a few today. The Batatacan study basically resulted in making the Park Service happy because we got most of the wood sample that was capable of yielding dates, and managed to make some discoveries about Batatacan itself that were new. Let's cover a couple of them. This is Batatacan in its rock shelter, one of the most spectacular sites in the Southwest, and in fact my favorite for its setting. One of the things, I apologize for the slide, but one of the things we were able to do is date individual rooms in the site as to when they were built. And we discovered several things. The one I want to illustrate here is that you can actually build a sequence of room construction, or in this case, room cluster construction. It turns out that these large Lake Pueblo cliff dwellings and open sites were not jumbles of rooms, because the rooms were formed into what we call room clusters that were functionally separate from other room clusters. And so we've got a whole series of these. They had not yet been demonstrated as to how important they were, but what you could show first of all was that these things existed in the space of the site, that the site is composed of room clusters, and then with the tree ring dates we could look at the dynamics, and in terms of the behavior, the human behavior associated with that, they were just as important, as significant historically as they were structurally within the sites. The things melded perfectly. We'll get to that more later. One other thing we learned there was these are plots of the number of tree ring dates from Batatacan up there and Keat Seal down below, Keat Seal being the other gem of Navajo National Monument. And they showed two different things in the way the human occupants of these sites treated wood. You see that down here at Keat Seal on the bottom, if you ignore that early part, the solid lines are number of tree ring dates per year, and these are projected population curves. And you'll notice that here, the major, except for this part here, the major increase in construction and population occurred at exactly the same time as a peak in wood tree felling. And then you get variations after that. Batatacan's quite different in the sense that you get this huge amounts of wood procurement, tree felling, but the population lags behind that, which means that at Keat Seal, they were not stockpiling. They were building stuff with these logs they acquired right almost immediately, Whereas up here, they were cutting trees and letting them lie around for a few years before they were actually used. So you get two different behaviors toward wood resources there. Combining the architecture with the dates at Batatocan, it's clear that what you actually had going on here is that these people moved in early in the right around 1260, most of them. These little groups here. And they actually were cutting these logs into standardized lengths. Big ones, long ones for primary beams, and other ones for secondary beams to be used later on. So they were building a stockpile. And that's why all the rooms in Batatocan are the same size, because the roof beams were pre-cut to these dimensions. A lot of other stuff came out of this study, but I'm not going to linger on that. You might wonder how all this stuff related to Rainbow Bridge Monument Valley expedition. In a lot of ways, the Rainbow Bridge Monument Valley's area of interest, that is from Rainbow Bridge to Monument Valley, corresponds extremely well with what's called the Kayenta branch of the Anasazi cultural tradition. So they share that geographic unity. My work shared a lot of the research questions that Rainbow Bridge was interested in. Furthermore, there's a ubiquitous presence of Rainbow Bridge on the landscape and elsewhere in that area. RB numbers all over the place on cave walls and stuff where they put their number on the sites. Everywhere you go, you see these things. And direct remnants of their field camp in Water Lily Canyon. This was what they called Camp Anasazi. So this is the area they and I have been concerned with. I've labeled the Kayenta branch up there. Over on the upper here you have Mesa Verde, Chaco, Kayenta. Tusayan and Kayenta are really very similar, except Tusayan lasted longer. And the Virgin branch is sort of an attenuated Kayenta branch. So. But the area of interest is very similar. Another interest we hold in common is dendroarchaeology. The Rainbow Bridge Monument Valley expedition, especially in their first 2 years, were involved in the collection of archaeological tree ring samples, quite apart from the survey they were doing and quite apart from the excavations. They spent a lot of time wandering around Sagi Canyon getting cores out of the cliff dwellings there with a major project at Keats Seal.
Did they basically use a standard technique that you then followed years later in terms
to take the
getting
samples?
Core samples?
Yeah.
I mean, we've established how to do that, correct?
Yeah, they were using a hand-driven 1-inch diameter tubular saw to take their cores. We had ours hooked up to a generator, but it was half as big, half-inch in diameter. But yeah, same thing, same technology.
You say it's abandoned after the Museum of Northern Arizona relinquished control?
Yeah, for the first 2 years, the project was actually supervised in the field by the Museum of Northern Arizona by Harold Colton, and Lynn Hargrave was the field director. And they reoriented RBMV considerably after the first 2 years, and M&A fell out, and Ansel Hall took more direct interest or control of it, and they changed what they were doing.
Keep the cores?
Oh, sure. No, they added, M&A had a collection of archaeological tree ring samples that they collected them and dated them, and then in the 1950s they sent all their stuff to us, so we have that now. This is just to prove they were doing tree ring dates. I apologize for the picture, but that's Lynn Hargrave gazing at a wood section cut from a stone axe cut beam end in a site in Sagi Canyon. First, and Rainbow Bridge and me and I have been interested in the environmental component of what humans were doing in that part of the world during their occupation there. And all archaeologists, even back then, were interested in what the environment was like and its effect on people that lived there. And so Rainbow Bridge was carrying on that particular tradition. The Cayena branch was and is a daunting place in which to make a living if you're an agriculturalist, a subsistence agriculturalist. It's not a forgiving area to do that stuff in. It's far less suited for farming than the other major prehistoric Puebloan groups faced, such as Chaco and Mesa Verde. It was a lot more difficult, and the environment played a much bigger role in Cayena than it did in Chaco or Mesa Verde, which is one reason why it's not a good idea to try to use what's known about Chaco and Mesa Verde archaeology to explain Cayena. It doesn't work. No, it does not. By and large, I mean, they're basic similarities, but just consider this following view of the landscape up there. That's not a great place to try to be a farmer in. A lot of it is just bald rock, no soil, no nothing. It ranges from really fir forests at high elevations down to 3,000 feet or so with other mountain ranges and so on. But it is a really spectacular area. Unless you're a farmer trying to make Anyway, the area, so I've pursued, and I hope refined what the Rainbow Bridge was doing. And just to set the background here, I want to talk a little bit about the environment. There are 3 stable environmental habitats in general. This is real rough in the Cayena area. The first of these are uplands, 5,000 to 8,000 feet in elevation, with sagebrush covered valleys separated by pinon juniper covered wooded ridges, lots of bald rock as you saw, paucity of surface water in springs. They're arid and cool, and they culminate in Navajo Mountain. This is what an upland area looks like up there. So you can farm out here in these flats, but it's not easy. Then there are lowland valleys. These range from 5,000 to 6,000 feet in elevation. And you'll note that the actual elevations overlap. Some highlands are lower than the lowlands, but it's the local topography that determines what is what. These are broad open valleys with more varied resources than uplands and generally comparatively abundant soil and water, as seen here in Longhouse Valley. Wide valley floor that's got lots of land in it. It had at certain times a fair amount of water with wide bounding walls on either side. And in this case, lots of domestic water resources over on this side, springs and seeps and what have you. Also in the lowlands, we have canyons that are roughly the same elevation as valleys, but they differ in being very confined between usually more or less vertical rock walls, so that arable land is limited to what's down there in the bottom. But they do have the greatest variety of natural resources such as berries, grass, wood, pinon, juniper, sage, timber, fuel, and water. And it's fairly easy to access, go from the lowlands to the highlands. You just have to climb up those vertical cliffs using hand and toe trails, but it's, it's only a short distance horizontally. And some of these canyons are uninhabitable due to soil and other problems. This is Paiute Canyon, showing that you can grow crops down there today even, or a few years ago. And within that general topographic environmental type classification, the climate is pretty much similar all over the place, 6 to 15 inches of rain per year. It's bimodal, peaks in the summer and the winter, and has winter frontal storms that move slowly across the area and saturate the soil. And then summer convectional storms in the summer are more localized with much more energy. It really rains hard, and but you need both those peaks in order to grow crops under conditions of the, let's say, the 13th century, because the winter peak contributes water to the soil that's stored to get the crops through the spring drought. The seeds are actually planted in the spring drought, but there's enough groundwater to keep them growing until you get through that time period, and then the summer rains start. But you also have to have the summer rains, because even if they germinate due to the winter rains, that water runs out, and if you don't get the summer storms, then the crops won't mature, or they won't produce as much. Temperature is pretty much adequate for a growing season of around 160 days, which is fine for the crops involved. But as both Rainbow Bridge and lots of people realized, you can't rely totally on the modern and present environment to characterize the past, because it's not stable through time. It changes, just like it's changing now. So that conditions at one time are not the same as they are 100 years later. And in order to study this, we've divided the continuum of variation in various environmental variables into low and high frequency categories. This is just arbitrary. Low, high frequency have a controlling environmental control of 25 years or less, whereas low frequency is due to processes that have a periodicity of longer than 25 years. Low frequency variation involves the accumulation and erosion of sediments along the floodplains. The ground surface you see there now was not there in 1300, because, as we'll see, it varied considerably. And the level of alluvial groundwater follows the rise and fall of floodplain deposition and erosion, so that when you're getting deposition, water tables are really high, so things are good for farming. Then when you get erosion, you get arroyo cutting, water tables go down, and the water table can be 80 feet below the level of the land you're trying to farm. And high frequency variability is primarily climate, as we'll see. Once again, our BMV was a pioneer in this sort of thing, and we were aware that cycles of alluvial aggradation and degradation characterized the drainages of the area, because they lived through it, or people living there just previously to that had seen a situation where in the late 1800s, before you had alluviation and high water tables, but in the late 1880s, arroyo cutting cut through and dropped the water tables and produced channels. So they knew that these things varied through time. And so they glommed on to John Hack, who was working for Harvard University in the Hopi Mesas area studying Hopi farming, who had come up with the same idea about these cycles of aggradation, degradation, high water tables, low water tables. And so they invited him to come up to Tsegi Canyon and see if he could duplicate that up there, which he did. And this is a classic study in southwestern hydrogeology, I guess. That was the foundation for tons of future chronostratigraphic research in the region. And it's published in...
Can you describe what you mean by arroyo cutting?
Sure. At certain time periods, under certain conditions, you have deposition of sediments across the entire valley or canyon floor. So the floodplain is grading, it's growing, it's getting higher and higher because more dirt gets deposited on top of it. At some point, the system changes and you get gullies and arroyos cut through that leave these deep channels, as opposed to a level, more or less, canyon floor with no flowing stream. When you have aggradation, if you have degradation, you have this channel cut through the sediments down to bedrock, and then you have water flowing in the stream, but it's 50, 80 feet below the old ground level that you're trying to farm. And so arroyo cutting is not good. It not only destroys the farmland, but it removes the water you need from the soil to the channels, and they had no technology to get the water up to the level.
That's because of the unpredictability of water?
No, it's because, well, yeah, it's hard to say exactly what causes it.
Is it flash floods in the summertime or heavy
Doesn't seem to
storms?
be. I mean, they're the same, more or less, whether you have aggradation or degradation. There's very little evidence for what causes these systems to change, but they do fairly regularly on a 550-year cycle. And we're in an arroyo cutting phase right now that began in 1880. Well, it hit this area in 1880s. I'll show you a little bit more of that later. Okay. There was a hiatus, more or less, in the study of alluvial sediments in the area until the 1980s or thereabouts, 1980 to 2000, when the USGS Flagstaff office were advising NASA on conditions they might find on the moon. And so they took them out to a landscape around the Hopi Mesas that they thought was lunar. And the geologists were pretty bored with watching astronauts trudging around in the dirt. And so they noticed that they did have this evidence for this cycle of erosion and deposition and so on. And they got interested in that and talked the survey into doing a 10-year research or more research project on that to see if they could work out the timing and the processes and things that cause this sort of thing. The one thing they ran up against was that their dating wasn't that good or consistent across space. They were using radiocarbon dates and archaeological dates, pottery dates from sites buried in alluvium and stuff like that. And so they weren't getting the necessary resolution through time to determine what was going with what and so on. Until they discovered a bunch of buried forests where you find in the alluvium trees that were growing there at one time that were buried during periods of deposition and died. And there's, whoops, well, I got this backwards. There's one now. This is an arroyo cut showing a juniper tree that germinated. This is the root crown right here. It germinated when the land surface was right there. But now the land surface is up there. So if you could date the tree ring date, the germination date down here, you could date it to when it happened and also figure out a real accurate range of time involved in the deposition of all these sediments in that valley. Especially if you get lots of trees like this from one place. And then they also took pollen samples to get a pollen chronology from or pollen record of past.
Do you just extract the pollen from the soil?
Yeah. Mm-hmm. Yeah. So anyway, they looked at hundreds of these. And we did the dating for them and helped them sample that stuff and so on. And this is that surface that you see up there dates the 1880s when this arroyo began cutting. So everything on top of that is post 1880. And these things uniformly date around 1300. We also find other ones at a level up here that date around 1700 germination. So we can bracket these deposits between 1300 and 1700 and 1700 and 1900 basically and so on. With enough replication, you become to believe it. Okay, I'm going to back up here. Farther down in the column, we run out of trees. They rotted away. But what we have are buried archaeological sites. This is an alluvial column in Laguna Creek, west of Cayenta, whereas the base level of these alluvial sediments is down here, and this was all deposited over a period of years up to this level right here. And archaeologists were excavating sites buried in this alluvium. This is one of them. This is the back dirt from a pit house. P1 dated by tree rings at 850, so we know this was the ground level in 850 right here. Then there are sites, a couple sites up here with archaeological sites dating to 1000, and then the top of the surface there is around AD 1300. So this provides sequences of really good dates.
Is that Easter Flagstaff or west?
Along Seguida,
Oh,
along Laguna.
it's near Cayenta, just west of Cayenta, not very far. It's where the dam is, if you know where that is, that is used to irrigate around Cayenta on Laguna Creek. Now, let's see what we got here. We've looked at that. Okay, so this is a composite of what we found out. And I'm not going to bore you with the details of this, but what you see here are deposits of alluvium separated by stable soil forming layers, dated by archaeology or C14 dates or whatever. There's one here, and here, and here, and here, and here, this being the one at 1300. That should be 1300. And then there was an arroyo cut through there, going like this, leaving this ground surface exposed for a long time. And then that arroyo began to fill up, and that's where the buried trees are. These ones rooted around 1400, these around 1700, these growing on top around 1800 and so on. And so these allow us to date the whole column, or most of it. The implications of that for archaeology in the area is that if you're farming on the floodplains, which you're doing in Cayenta, unlike Mesa Verde where they farmed on the mesa tops, you're susceptible to these cycles of deposition and erosion. So if we start here at 1, this is the situation, let's say in AD 800 to 925. This is, in each of these drawings, this is a bedrock canyon, and these are what's going on in the alluvium. And during this time period, it was all eroded out, primarily. There wasn't any soil at all. This is the arroyo width. Then starting around 900 or thereabouts, or 950, you began to get deposition within this level here. And so and the dark area is the water table in the alluvium. And so with conditions like this, you can farm anywhere out there. Water table's high, you just plant your crop and you get corn. It culminates around 1130 with much more alluvium, but still the same water table situation. But then, where are we? Number 4. About 1150, you start to get a little bit of arroyo cutting. And then by 1250, you've got major arroyos forming. And as this happens, the groundwater level goes down. And so by 1250, the water table's here and doesn't contribute any moisture to growing crops on the floodplain. So you can no longer plant crops anywhere out there. You've got to find localities that are immune to arroyo cutting to plant in, and that represents this situation at 1300 up here, where this deep arroyo has taken the water table completely away. And again, only crops you can, places you can grow crops are where certain conditions inhibit the falling of the water table. And so using all this information, you can kind of predict where sites ought to be at certain times given this sequence of arroyo cuttings. And we did that, and we'll get to that later. And it turns out we were pretty good at it. Then we turn to high frequency, and this is mainly climate amplitude reconstruction. This is just a Palmer Drought Severity Index, which means that a high value things were good for growing crops and a low value means they were bad. And these are annual values, and so you can look at that sort of thing on an annual scale, just based on if they were relying on rainfall and temperature. This would be a good year, and this would be a bad year. If you're if you're isolated from the water table, they're all bad years. But that's a typical dendro.
At an absolute level, are those very bad drought years, or is that kind of just a cycle that
No,
can
it's
still grow?
no, it's a standard statistic ground out by the Weather Bureau or whoever they are, call themselves these days. Anything above +1 is considered to be good for crops. Anything below -1 is considered to be bad for crops. So you've got this band in the middle where things are okay. There are other important aspects of high frequency climate variability in addition to amplitude, that is how big it was, if there's lots of rain or a little bit of rain. These involve temporal variability, spatial variability, and coherence. This is a graph of tree ring departures on the southern Colorado Plateau from whatever AD 0 to 2000. And you can see these periods of time in here that are hatched are periods when you get rapid fluctuations from high to low values, as opposed to the intervening periods, which are much more gradual. So these are periods of high temporal variability, and these are periods of low, and so on. And if you got high temporal variability, that is, if things vary rapidly from one year to the next, storage is a good idea. You can accumulate stored reserves, and if you have a bad year after a good year, you'll have something there to use. If it's more slow, as it is during this period, you have to look at the trend, because the trend, if it's going up, it'll get better through time. If it's going down, it'll get worse through time. So you have to deal with a different system, more or less. So it has different implications for human behavior. Then you have spatial variability, whether it's low or high. This is a map of the northern southwest. Four Corners is up there where those lines cross. Each one of these is a tree ring chronology station, and these little triangles are the numbers, and these values are the standard deviations of the values for that decade. So between 1860 and 1869, things were pretty much the same everywhere. There's not a whole lot of variation between one place and another. So what that means for people is you don't get any large production differentials across space. So if things are good, they're good for everybody. If things are bad, they're bad for everybody. And so you don't get any movement of goods and or armies across the landscape, because nobody's any better off than anybody else. In contrast, high spatial variability, as in 1610 to 1619, you go from 7.3 standard deviations above the mean right here to 2.2 below over this space of a very short distance. When you get conditions like this, these people are really good, doing well. These people just a short ways away are doing terrible. And so these differentials create pressures for either these people here to trade goods of some kind for food, or to go out and take it away from these guys, which is a completely different response than you would get if you had low variability. So each one of these, the important takeaway here is that each one of these different measures of environmental variability, either low or high frequency, specify different behavioral responses to what's going on.
Jeff, what are the contours? I mean, why do you have a concentration of contours around?
They're one standard deviation unit.
Okay.
So this would be 7 plus, and this would be, I think,
It's measuring variability.
yeah, that's all. How much this one, this is above the mean for that station. So it's way out of sight production-wise for that decade, whereas this one was out of sight in the other direction for that decade. And then there's this little gem. Another aspect is what you could call spatial coherence. That is how the tree ring chronologies across this region vary together through time. And this is a snapshot taken between 966 and 1988. That is the length of the record, basically, that shows that over that period of time, you had, these are principal components analyses of statistical things. What it means is that these stations in this area were behaving in similarity to each other. That's the first, that's the second component. These stations up here were bearing similar, were behaving similar to each other within this area, but differently from these. And so you've got these two components, one on the northwest, one on the southeast, that are take this form, including stuff way up in Utah is included with these stations in the southwest and so on. So what we got are these two areas that are behaving similarly to each other, like within but differently between. And we also noticed, we plotted modern records for the last 100 years or so to see how seasonal distribution was of rainfall in the southwest, and you get something like this. So that over in the southeast, you get summer dominant precipitation. Over up here in the northwest, you get bimodal precipitation. And that looks a heck of a lot like that distribution I just showed you for the whole time period, indicating that this is, and this is a pattern that lasted a long time. It's a pattern that farmers would get used to over the years, and this is what a specific 100-year period in the middle of this time range looks like. It's very similar. The stations are different. The ones that behave together vary, but you always get this S-shaped dividing line, and you always get a northwestern one and a southwestern, eastern one. And sometimes they don't go with anything like these. But that indicates that you have, this is a pattern that has persisted over at least the last 1,000+ years, and that people would adapt to that. And so that's fine. You're going along just fine, doing what you do with a bimodal distribution up there and a unimodal distribution down here, and all of a sudden you find something like this that makes absolutely no sense whatsoever. You got Durango up here behaving with Flagstaff, Coconino Plateau, the northern mountains, central mountains, the southern central mountains. You got this unit, these two up here behaving with these up here. These up here go with Mesa Verde, which doesn't go with anything else, and so on. It's just a total mess. The only thing that persists, I mean, this is a total breakdown in the pattern, except the southeastern one is always there. It doesn't break up like the northwestern one does. And we think what's happening is that for this period between 1250 and 1450, for 200 years, the seasonal patterning of rainfall in the northwest just went to hell in a handbasket. They could no longer rely on that on the two peaks of rainfall anymore. They got weird stuff that is going on and represents totally different conditions than before. Whereas down here, they're still doing well with a unimodal summer for that 200-year period. And I should mention that during that 200-year period, much of this area was abandoned. And where did people go? A lot of them went down into here, where things were more stable. And there were populations there that could deal with those conditions, and they joined them. And then after 1450, they never did go back up there to speak of. But they didn't go back up there anyway. I mean, now, you can combine all these things into measurements that are for comparative purposes. The A graph shows the deposition, those uplimbs, and degradation or erosion going down and up and so on through the last 2,000 years. And you can see a regular cycle of about 550 years to the present, which is down. And so you get periods of deposition and separated by periods of arroyo cutting and degradation. The hydrologic curve shows a remarkable parallels this in a remarkable fashion. This is the high water table, low water table thing. So when you get high water tables, you've got high, or when you have aggradation, you've got high water tables and so on. And then we've got the spatial, or the temporal variability, spatial variability down here, plus other indicators. And what this allows us to do is combine all these measures and identify periods of time when things would have really been bad and periods of time when they really would have been good. And you can use those time breakdowns to predict what people would have to do to survive. And you can also rank them into the worst to the best or whatever. And if you do that, the worst time period environmentally in that 2,000-year period is right there. So it's, you have arroyo cutting setting in, you have falling water tables, you have falling effective moisture, you have change from low to high temporal variability, you have high spatial variability. All that stuff combines to indicate that this is the worst time period in the entire period. Second worst is right here. Low, major drought, effective moisture is falling, there's a drop in the water table and a pause in deposition. That's the second worst, and so on. And what do you think this one corresponds with? It's the abandonment of the northern Southwest by Puebloan people around 1300. So we predict it would have been bad, and it is a major upset of in human demography and all sorts of other variables that happened at that time. It was
Can
exacerbated.
you confirm any of that from tree rings?
Well, yeah, I was about to say. This, where are we? This is the, right there is the Great Drought of 1276 to 1300. That adds that, you add that on to the other indicators. Plus, that's when that spatial patterning of seasonal rainfall broke up. All that stuff hit them all at once, and populations were at their maximum. The place was full of people. There was no area where there weren't people up there anymore at that time. And so they were pushing the carrying capacity of the whole zone. And what happened was that all these things happened at once, and they lowered the carrying capacity below what the environment would support. And either they had a choice of staying there and a bunch of them dying off, or moving to some place where they could survive. One being the Rio Grande, where they had the unimodal thing. The other being the mountainous area along the center of Arizona and New Mexico. And the Hopi Mesas area is another one, and so on. That's exactly what they did.
And so what you see in the tree rings is the lack of moisture,
Yeah,
or you can see all these variations.
yeah. Well, the tree ring record tells you, yeah, whether it's raining, you're getting a lot of rainfall or not. But these other things make that worse. If you get all these other things combined with the drought, it's worse. A drought by itself, if it corresponds to a period of high water tables and stuff like that, it's not going to have much effect. And just to look at the second worst thing right here, this was a period of major cultural change across the Southwest. Right around the mid-1100s, Chaco collapsed. Classic Hohokam collapsed. Populations generally started abandoning higher elevation areas and moving down to lower elevation areas, and so on. So that period too is accompanied by,
The first one you said 1276?
well, 1276 to 1300. That's the Great Drought, but its period is actually longer than that, because that disruptive period lasted from 1250 to 1450. So that was 200 years. Okay, how are we doing for time? So that's the major outcome so far of all this paleo-environmental research that we did in the Colorado Plateau. That was more or less a outgrowth of RBMV stuff back in the 30s. Any questions so far? I mean,
Jeff, I know it's very granular, but are you extrapolating any of this into today's shifting climate?
no, because it looks like it's a major, looks like the limiting conditions that establish an environmental system have been breached, which they weren't during any of these periods. So we've exceeded the limits on what defines the average environmental conditions. The whole thing is shifted up. And so you get, the whole weather stuff, particularly that we're putting up with now, because the limiting factors that control the boundaries of these things have changed. We're in a different system, and it's pretty clear that you can't compare the two, really.
But you're studying the present, though, right now? I mean,
Yeah.
the last 50 years and...
Well, since 1976, basically. It began, you can see it began in hindsight around in the 1950s. Things started to go a little screwy. But since 1975, all over the world, hundreds of environmental records indicate a major upward shift, or let's say badward shifts. I mean, some things went down, but they were not good. So, and we've got, like I say, hundreds of records of different kinds, glaciers and all this stuff. All the glaciers are melting, sea levels going up, the oceans are getting warmer, all this stuff going on. It looks like the whole system has changed. Luckily, it doesn't affect the prehistoric people of the Colorado Plateau. Looks like stability was established sort of at the end of the Pleistocene, 10,000 years ago, in the Southwest, and that things varied a lot, but they were between limits that were stable up until 1950, let's say, and then they started to go haywire. So that's a long period of stability for people to develop ways of dealing with the environment and getting crop production and things. Then all of a sudden everything changed. Okay, complete change of pace. Whoops. Another research aspect that RBMV was interested in was what the populations of that area were doing through time. And I'm only going to look at the last little bit of that time period. The Kayenta branch Segi phase, which lasts from 1250 to 1300. It's the culmination of developments that began 4,000 years ago when they started growing crops, and and this is the end of it. And so what we get by the time of the Segi phase in the Kayenta area are, this in terms of settlement now, I'm not going to cover everything. Settlement hierarchies exist, going from the simplest to the most complex. You have room clusters, which equal households. Then you have small residential sites, you have large residential sites, something called central pueblos, and site clusters focused on central pueblos, and then multi-cluster communities and multi-cluster communities. These are all ascending levels of social integration. So this is a room cluster. This is 4 room clusters. And they all take the form, more or less, of, let's look at this one up here because it's the best, of a living room, some granaries for storing food, focused on a unroofed courtyard. And you can see the same thing here, living room, courtyard, granary, granary, courtyard, courtyard, granary, granary, living room, granary, granary, living room, and so on, at 4 different sites, Keats, Seal, Batatican, Batwoman House, and Scaffold House. These are the building blocks, Segi phase pueblos. And they equal a household, basically. So this is what one looks like in the flesh, so to speak. You've got a living room here, and 2 granaries that open onto a courtyard that has no roof, and it housed a family of X number of people. Next step up is just these little pueblos that are all over the landscape. Some of them are just a single room cluster, others are just 2 or 3 or 4. And then we get larger sites such as Keats Seal, and you can see those dark lines outline the room clusters within the site. But the site as a whole is a step up from small sites. And then we have central pueblos, which in this case is also a really big site. This is Longhouse in Longhouse Valley, 300 and some odd rooms. It's the biggest Kayenta branch site known. And the central pueblos are the focal unit of clusters of sites. You'll have a central pueblo located on an eminence next to, and then around that you will find regular residential sites, usually at a lower level. So you've got a special site that was communal with other sites grouped around it that form this other level of multi-room cluster sites. And the characteristics of these things, they all have the same characteristics. First of all, they have a large room, sometimes with cross walls, sometimes without, with massive architecture, massive walls, unlike the regular walls, fronting a plaza. This is called the well, for simplicity, we'll call it the spinal room block. Focusing on a pueblo, and in this case, it includes a heck of a lot more than that. You've got all these domestic rooms here, some with plazas and so on, trails that go into it, and a corridor up through there to the plaza, and a reservoir, which is over there, so up there. And those are general attributes of a Segi phase site cluster central pueblo. This is the same one. This is Longhouse. It's sit up on this rock on the edge of the valley in the floodplain. It has a spinal room block here, 90 feet long, walls are 10 feet high, and then all this is architecture. All through here. This is all subsidiary sites. And then there's a trail in that way, and the trail goes up here, dam here, and a reservoir there. That's the granddaddy of all of them.
Jeff, did the structures help preserve that, I'll call it a butte for one another? In other words,
No, I don't think so.
you don't think so?
It's solid rock. What's on top of it is masonry, architecture, and trash, human occupation debris, but it's just this stuff.
Can I ask you a question? So the plateau, the house area is at the base of a cliff?
No, this is actually this actually projects above the landscape. There's a
Okay, thank
gully behind this. And so this is the central pueblo here, but these are all smaller pueblos around here. Then this is the rock drops off. You can see it a little better in the next picture, I think.
There's kind of an empty space behind it.
Yeah. This is what it looks like from the valley floor, just to show that it's on an eminence and that there is nothing behind it. This is a trail into the site. These are all rooms up here, and that central pueblo is back behind. You can't see it from here. But that's all those central pueblos have these attributes. And they have walls like, none of them have walls like this, but they all of them have double wide or triple wide walls. All central pueblos do, and other ones don't. Longhouse is just grander than any others. And then here's the reservoir. You can see the water line on the bedrock. Then the next step up is the group, is the cluster of sites around the central pueblo. Here's Longhouse here. And in addition to that, there are sites all through here, Segi phase sites, that are focused on this, and usually you can see the central pueblo from wherever you're living or along the valley here. And then a step up from that are site clusters. Those were site clusters, and here they are. You can see these here's the Longhouse site cluster. Here's another one with their central pueblo. Here's another one up there, and one over here. And those represent the site clusters within the valley. But if you actually take the trouble to go up to one of those sites, you'll discover that from each one of those you can see all the others. These are situated just where you can have to be to see this one and this one and this one. If this site was back further on level ground, you couldn't see this one. Instead, it's stuck out here on a sloping thing, and then there's this one up here that probably can be seen from.
Does that mean you could also hear the other side?
In this case, yeah. Longhouse Valley is not that big, so if something was going on here, you could hear it from Longhouse easily, or vice versa. You might not be able to hear something going on up there down here, but the line of sight thing looks like this. You connect them all together. And this is a multi-cluster unit. In this case, it's the valley. But there are others just like this everywhere you go. Some of them a lot bigger than this, like up around on the eastern side of Navajo Mountain. There's a system so large you couldn't possibly hear anything that went on in one site from another site. But what they do have is that the whole system is focused on this rock. Sticks up out of the top of Paiute Mesa, and on the Hand and Toll trails go up to the top, and on the top you can see where big fires were built. So
Jeff?
they were signaling, yeah.
Jeff, is this unique to this series of settlements, or is that something that's found in other archaeological sites?
Well, I don't know. This exists wherever you find Sagi phase sites. And usually, I know of 1, 2, 3, 4, 5, 6, 7 or 8 of these systems. I've not looked anywhere else. I don't know whether they're elsewhere or not.
That's, Segi Creek comes in right at the very top there.
Yeah, that's Sagi Canyon right up there at the top. That's the mouth of Sagi Canyon, the marsh pass right there. And then there's some evidence for multi-cluster sites, because from this site up here, you can see all the way to Kayenta, and a rock just to the west of it, on which is the central Pueblo, and you can see from one valley to the other. So there are bigger line of sight communication systems. Here's what it looks like in the valley. This is one central Pueblo here. From there you can see Tower House and you can see Longhouse. The other one's over here.
I'm sorry, Jeff, are these conclusions that were drawn from the Rainbow
No.
Monument Valley, or by you?
By us. We just discovered this whole thing about starting in 1965 or thereabouts. In fact, we predicted this site. We were standing on Longhouse one time and realized that you could see Tower House from there, and you could see this site from there, and we predicted there ought to be one down here. So we went, picked the nearest appropriate place, walked there, and there it was.
You started in the 1960s, did you say?
Yeah, 65 to be precise. I can tell you the day if I had my notes. We were out looking at buried archaeological sites and with a couple of geologists, and then
There's still a dirt road through there.
through here,
Yeah, through Longhouse Valley, goes to Canton.
there's a paved highway.
It's paved.
Yeah,
Highway 89.
yeah. It's right over there. Yep. So if we, before we move on, hope I'm not taking up too much time here. We should look at the end of the Kayenta branch. Because by 1300, the area was basically totally abandoned by agriculturalists, or at least Puebloan agriculturalists. And that leads to two questions: is A, where'd they go, and why'd they go? And so recent research has proved some answers to the first question of where did they go. Not all of them, but where did some of them go? So when tracking Kayenta immigrants across the southwestern landscape, we have all sorts of evidence. Masonry pueblos in non-Puebloan contexts, that is site unit intrusions where you find a Kayenta site plunked down in a pit house village somewhere. Identifiable enclaves of Kayenta people within larger local sites, such as at Point of Pines in Arizona. Kayenta Tusayan kivas, one of which is due east of Tucson, across the mountains in the San Pedro Valley. Unique Kayenta architectural features, especially the entry box complex. Kayenta Tusayan ceramic attributes, perforated plates. Kayenta pottery imported into these new locales. Local copies of Kayenta pottery at these places, and ceremonial imports, plus other minor things. This is the latest rendering of what this must have looked like on the map. You get these people moving out in all these areas down south. One Point of Pines here was probably a secondary dispersal point. There is a large Kayenta population that moved down here and then probably spread in this direction, clear down to the Reeve Ruin, and in the San Pedro Valley, and Tucson's right there. And Mexico is right there. These are recognizably Kayenta.
They also went to Hopi. I mean, that was
Well, they went to Hopi first. I mean, and some of them undoubtedly stayed there, but then they moved on, a lot of them. Yeah, they did go to Hopi, and a lot of them actually dropped off there and then moved farther south. This is a site unit intrusion. This site over here is on Paiute Mesa. It's a Tsegi Phase site called Meskai Village. This is a site outside of Safford, Arizona, the Goat Hill site. You could drop one on top of the other and not. And there are several.
Is there any indication that those migrations were met with opposition, or did
Actually, not well. No, not really.
how did they do that?
I don't know. That's one of the mysteries of South. Why the Canada can do that? You can track these people for miles, miles, hundreds of miles across the landscape. You cannot track Mesa Verde people anywhere. Mesa Verde archaeologists say, well, they all went to the Rio Grande Valley. But if you ask a Rio Grande Valley archaeological specialist, they say, no, they're none of them here. So you just cannot find Mesa Verdeans anywhere outside
Is
of
there
it.
any signs of conflict between those
No.
when they were absorbing
No.
populations into one another?
None that we know of.
Couldn't that be tracked with DNA?
Well, it could if you had any burials, but we don't.
Well, I mean, Cayenta, there must be some.
There are some, but I don't think they're enough to do you much good. But yeah, you probably theoretically, sure, why not? This is a. What do you think that is? That's a kiva. And where do you think that is? It's across the mountain from Tucson.
I don't have to go in the tournament.
But there's no doubt it's a kiva, and it came from up north. And then here's what's called the entry box complex. Is pure Canada. It originated in the Canada area and is found as far south as Tucson in sites. Perforated plate, pure Canada, again, found all across the southern Southwest. Don't ask me what the perforations are for.
Okay.
Nobody knows. Or even what perforated plates were for.
They get to Pacume?
Yeah, I think so. Yeah, I think they did. Yeah, I wouldn't swear to it, but they have some have been found in northern Mexico. And then there's local copies of Cayena pottery. This thing here is from Kanishba Ruin on the Fort Apache Reservation. Made by a local potter who obviously was trying to render something like this genuine Tsegi Phase black on white jar and failed miserably. But you get a lot of these local copies, both in black and white and stuff like that. But that's a real thing over there. This is a local copy. And so are these, but in polychrome. Keat-Seal polychrome over there, Tucson polychrome over here from southern Arizona, and design styles and everything are almost identical. Ceremonial goodies over here. This is the famous Sunflower Cave cache that Kidder and Guernsey found in a rock shelter in Marsh Pass in 1914, containing hundreds of these flowers, both made out of leather and out of wood, and other carved birds like this, many of them in these things, whatever they are, in a pot, buried in a cliff dwelling. This stuff came from a pot buried in a cave on Bonita Creek north of Safford in southern Arizona, with stuff that's almost identical to that. And this is where they ended up, which is a far cry from the Cayena Branch area. This is the San Pedro Valley. You don't have these cacti up here in the Cayena area. Okay. Quickly, one of the major issues of southwestern archaeology right now is how can you account for the persistence of Cayena traits after they abandon the Cayena area and they keep turning up all over the place. And these are the things that people have come up with. One is that Cannons were highly mobile at all levels of their society, households, villages, communities. They moved around a lot. They were adept at combining and recombining households into different configurations as situations demanded. They were flexible. Social variability. They weren't locked into rigid behavioral configurations such as was the case in the Mesa Verde area. And they probably had prior experience at integrating other people into existing settlements, from incorporating immigrants, probably from the north, Bears Ears, anyone, who contributed to the population increase and cultural variability of the Segi phase. And all this stuff endowed Cayena with a degree of flexibility not common in other ancestral Pueblo peoples before 1300, or even after. Okay, now, one more thing, and we'll be done. The Artificial Anasazi Project attempts to answer aspects of the second question, that is, why did they leave? This is a joint effort of a lot of people from Southern Illinois University, the Brookings Institution, the Santa Fe Institute, School of Advanced Research, the University of Massachusetts, and the Tree Ring Lab. And the mechanism we chose for this effort was an agent-based model developed of the form they developed at the Brookings Institution. And we chose Longhouse Valley as the test bed for a lot of reasons. It's self-contained. We had a 100% survey of the place, so we didn't have to make any projections, and so on. An attempt to develop a model that replicated the actual situation and events in Longhouse Valley. We ran the model to see if we could replicate what the real people in Longhouse Valley did. And it draws together most of the approaches I've talked about so far. So this is kind of where it all comes together. And this sort of represents the basis or the conception of the project. This is a picture of Longhouse up there, out in front of it, a field of corn. And if you took this picture in 1275, you'd probably see much the same thing, except there'd be a complete pueblo up there with people living in it. But we're combining aspects of the environment as it affects corn production to predict what the people were doing in Longhouse Valley. Operations. First of all, you have to construct a production landscape. If you're going to do one of these, you have to develop a model of food resources. In this case, we used corn as a proxy. So we combined relevant paleo-environmental data, especially annual precipitation and floodplain aggregation based on all this stuff I've been talking about, across 5 different environmental zones in the valley, converted the above into corn yield in kilograms per hectare based on all sorts of data. We then took this production landscape where we showed the production of each hectare for every year from AD 400 to 1980 or whatever, and populated that landscape with households that were, we picked a time, and we started AD 800, and we looked at all the households that were on the valley landscape at that time and put them in the model where they were at that time. That was a starting point. And then the households come into being, they grow and decline and die out over time according to logical population curves. Each household consumes a certain weight of corn per year per person. The model tracks the amount of corn in storage through the years by subtracting consumption from stored reserves. And in April each year, the household calculates the amount of corn they will have to grow to maintain a 2-year surplus reserve in kilograms. Based on those calculations, each household predicts if they can grow enough corn in place where they are now to meet their target. That is, based on last year's production at this place, can we expect to get as much as we need for this coming year? And based on those, and then if so, they stay where they are. And just go on as they've been going on. But if not, they move to an unoccupied spot on the landscape, that is, there's no other site on it. that they predict will provide a suitable crop to meet their target and maintain prescribed distances from the nearest other sites and prescribed distance from a source of domestic water. Households that fail to meet expectations disappear, that is, they die or migrate out. We don't specify which. And the program tracks the land occupied by each household and population growth or decline from one year to the next. So outcome, number one, we run these models over and over again, so we get numerous runs, sometimes it might hurt, sometimes fewer. And most of them replicate various attributes of what happened in the real world, like population growth, population movement within the valley, spatial distribution of sites through time, size distribution of household clusters, selection of farming locations, and amazingly, and I think it's amazing, every single one of these predicts longhouse. It shows the biggest site invariably is in the model is exactly where longhouse is every time. Yeah, that's what we see. Outcomes 2. The simulation doesn't replicate the actual abandonment of the valley around 1300, and we didn't really expect it to, because we already knew that you didn't have to, all of them didn't have to leave. Instead, the artificial people responded in a way that made ecological sense. Instead of carrying on as usual, they did 3 things actually that allowed roughly a third of the population to remain in the valley. 1, they sloughed off 2/3 of the population. They left. 2, they gave up living in large, unsustainable communities and dispersed into smaller settlements that were 3, located in fewer places on the landscape that would have remained agriculturally viable given the radically altered conditions after 1270. That is, sustained drought and royal cutting, depressed alluvial water tables, erosion, and all that other stuff I talked about. We all thought that, well, this is far more interesting than the successes. But what it made us think is that we have a pretty good understanding of about the human demographic and adaptive dynamics in Longhouse Valley and by extension the Kenai area. This wouldn't work for anywhere else. But as I say, the failures are the most interesting things. The consistent results establish that while approximately 2/3 of the abandonment of the area can be attributed to environmental push factors, a third can't. It was due to something else. But a third of the people didn't have to leave if they were just there to stay alive. The rest, however, likely were due to non-environmental, mostly cold, sociocultural factors. Okay, this just shows the change in population distribution from 1150 to 1250 over here, 1250 to 1300 over here. I've shown you this one already, but the model consistently reproduced this change where the population moved to the north, where it clustered in these clusters, where it did everything that didn't happen back then, centuries previously. This is the population curves compared, the real versus the model. The real one is the red line. So here. And the black one is the simulated population through the same span of time. And you'll note that the gross features of these things are almost identical. This one's smoother than this one because it's dating. Ceramic dating doesn't allow, it involves a change from one phase to the next, so basically you just need to move this down here. But this you don't have that problem since you're working on an annual scale. But the large scale thing is this big hump prior to 1150 or thereabouts, and the same drop, and then this rise again, and the same drop, off in time. But the big difference is that whereas the real population went to zero, the modeled population continued on. And although it's much less than it was before, at this point, people could have continued living there without too much trouble. If they were willing to make these changes in society. Show this, but it's the best I got. These are site sizes and through time by the simulation. These are big sites. You can see they aren't very many, and they shoot up and go down, and eventually down to zero. Smaller sites at this size go along nicely, but right around here, they begin to increase in number. And so this shows that they couldn't maintain the big sites, but they could maintain these medium-sized sites at a lower level of population. They chose not to. Okay, causes. Massive environmental deterioration, I've spoken about in the late 1200s. High population levels that approached or exceeded diminished carrying capacity, but they're not sufficient to cause total abandonment of the valley or the region. It a long time was thought of as an aberration of some sort. But now archaeologists are trying to integrate it more into the general pattern of Puebloan archaeology with some success. But they're, rather than looking at it as some sort of freak, you know, people spend years looking at these and they don't look at anything else down there. But taking a look at the whole picture, you actually have canopy in this area from the west, from into New Mexico.